Okay, so now I'm going to talk about the classification of compact two-manifolds. And so before I do that, it's like I'm going to first show you how you can construct some basic two-manifolds by identifying sides of a square. Okay, so some sort of basic two-manifolds can be obtained by identifying sort of edges of a square, and we've already seen a few. Let me just try to enumerate all of them. Okay, so there's the sphere, where you do this reverse orientation, and again another reverse orientation here. This is S2, the sphere, two sphere, if you will. Right, then there's the torus, which so if you prefer, this is sort of what I'm thinking of. Okay, so the torus is obtained by identifying the opposite edges, but in a consistent way. Okay, so this is T2, and so it looks like a donut, or the surface of a donut. That's the torus. Okay, then there's the projective plane, P2. Okay, and you do this reverse orientation. Okay, so this, if you look at it, it is a little bit different because you'll see that individually it's like both of these things are reverse oriented. Okay, yeah, but it has to do basically what's happening at the corners. Okay, so yeah, so you have to do this identification slightly differently. And then the Klein bottle is the following: reverse orientation and then consistent orientation. Right. Okay. So the reason it's like the Klein bottle is less important, it's like for our purposes, it's like, but the reason why I wanted to talk about these three is because that's going to form part of the classification theorem. Okay, so the classification theorem then is that for compact two-manifolds is that they can be obtained basically by sort of considering these three, it's like, and as well as connected sums of them. Okay. Okay, so the compact two-manifolds with boundary, without boundary, sorry, are given by the following. And so it should be understood, of course, that when I say that they're given as this, it's like I mean that any compact two-manifold without boundary is homeomorphic to one of these things, right? Okay, so there's the two-sphere, okay, S2, and then there's the torus, T2, and then you can look at these connected sums of copies of the tori, okay? Goes on, and then it's, okay, so these things are the orientable ones, and then they're the non-orientable ones, which start with the projective plane, and then sort of connected sums of copies of the projective plane. And so on. Okay? All right. So so the claim is that you know, if you have compact two-manifold without boundary, it's like then it's diffeomorphic. Sorry, it's homeomorphic to one of these things. Okay. All right. So we've seen how you can try to model. It's like you know, two manifolds is like by looking at things like squares and identifying things. So we're going to sort of look at a slightly more general construction where instead of looking at the fundamental object as a square, we're going to try to work with triangles, just because it's a little bit easier to attach triangles in sort of an arbitrary way. Okay. So this leads to the idea of a triangulation. Okay. So, and this is going to be important because oftentimes we're going to work with triangulations in order to compute. It's like these various sort of topological invariants, all right? And one of the consequences of something being a topological invariant is that the thing you end up computing is going to be independent of the choice of triangulation, okay? So first, let me see what it really means to triangulate a two-manifold. So to triangulate a two-manifold, right, we have to decompose it into regions that are homeomorphic to a triangle. Okay, and then what happens then is that we're going to associate to each region a geometric triangle, and then we're going to associate to each region a geometric triangle. Okay, so let me sort of try to draw a picture for you. So imagine you had the sphere, okay, and all right, so imagine you had these dots here. Okay, I'm going to think of something like this, right? So this part of the okay, so this piece here, right, is something which geometrically, or which is homeomorphic to a triangle. Okay, so I'm going to identify it with something which is geometrically a triangle, which is something like that. Okay, so that's what I mean by here. It's like I have a region, okay, which is homeomorphic to a triangle, and then I associate to this region an actual geometric triangle. Okay, and so I keep doing that, right? So so I have these 4 points. It's like on the equator, and then the 2 points at the north and south poles. All right, so I'm going to do, I'm going to sort of, I'm going to look at another triangle, which is this piece here, right? Okay, so this piece corresponds to this triangle, this piece corresponds to this triangle. All right, and what's going to happen is I'm going to glue these triangles along their common edge. It's like in accordance with what happens the actual two-manifold I'm working with, right? So these two regions share a common edge. I want to identify these edges. These nodes, it's like are common. Again, I want to identify them. So I start with identifying it's like a geometric triangle each of these regions, and then I look at how it's like in the original two-manifold these regions are connected to each other, and I want to connect these geometric triangles together in the same way. Okay, so So it's something like this, and then so this, for example, is an example of taking it's like this collection of regions and identifying with geometric triangles, and then sort of gluing everything together in a reasonable way. Okay, and so you can see this is a triangulation. And what has to happen, of course, is that when you glue them all together in the obvious way, it has to be that there is a homeomorphism between the original manifold, that's again this triangulation. Okay, so each region is identified with a geometric triangle, and we associate and we connect the geometric triangles in the same way that the original regions are connected. Okay, so what happens then is that, of course, each of these faces, each of these triangles is a piecewise linear space, all right? So, so we obtain a piecewise linear model. And this is a triangulation. Okay, if it is homeomorphic to the two-manifold. So in a sense, if you think about it, the fact that topological invariants are independent of the choice of triangulation is sort of tautologous, right? Because, I mean, by definition, a topological invariant is something, it's like, which is, you know, the same when you look at the equivalence class of manifolds which are related to each other by homeomorphisms, okay? So if you have a triangulation, right, and it's a homeomorphic to the original two-manifold, then in some sense, if you compute a topological invariant for a particular triangulation, it has to be the same value as any other triangulation, just sort of by definition of what it means for you to have a topological invariant. Okay. Anyway, so one of the consequences, it's like of this condition that it's homeomorphic to a two-manifold, is that when you look at the triangles, it's like of the triangulation, right? And you look at any pair of them. So this sort of implies that any pair, any two triangles, right, are in the triangulation are disjoint share an edge or share a vertex. Okay. With sort of an understanding that if they share an edge, I mean, it sort of implies that they share two vertices as well, but we only sort of are looking at the highest dimensional thing they share, right? So basically, it's not possible for you to share two vertices without also sharing an edge. It's not possible for you to share two edges without actually sharing the same face. Okay, and I should say any two distinct triangles, right? So it has to be that when you're looking at distinct triangles, they have to be either totally disjoint, or they share just one edge, or they share just one vertex. Okay. All right. And I should say that if you know something about what are called simplicial complexes, then you'll see that this condition here is going to be reminiscent, it's like, of one of the axioms, it's like, which a simplicial complex has to satisfy. And so we'll see more of this, it's like, as we go along. Okay, so anyway, so you have a triangulation, right? And so earlier on we were talking about this idea of the orientability or non-orientability of a manifold. So it's natural to ask that, well, okay, so if you take a manifold and you triangulate it, right, can you say something about whether or not that triangulation is orientable? Okay, so how do you do this? So given a triangulation, right, we can orient each triangle, okay, and then two triangles are compatibly oriented if they induce opposite orientations on a shared edge. Okay, so what do I mean by that? So imagine it's like I have a pair of triangles here, all right, with a common edge, all right? So of course it's like you only really care about pair triangles with shared edges, right? If they don't have shared edges, then you don't have to worry about compatibility of orientation. Okay, and so I'm going to, just for illustration purpose, I'm going to double this line, okay, just so that I can look at what the induced orientations are coming from the left triangle and the right triangle. Okay, all right, so an orientation is going to be an ordering of the vertices. Okay, so for now I can sort of orient this in a clockwise fashion, and I can do the same thing here, right? So it's quite natural to think of those two things as being compatible orientations of the pair of triangles. And let's look at what it induces. It's like on the edge, right? So if you look at this, you know, this, you have this clockwise motion, so it's easy to convince yourself, or it's easy to see that the orientation it induces on the boundary is given by the following. And the same thing happens here, right? It goes this way, it goes that way, and it goes this way. So if you look at this edge, right, from the left side, the orientation induced on that edge is going down, and on the right, from the right side, it's going up. Okay, so this is what I mean, that if you have two triangles which are compatibly oriented, then the orientation it induces on their shared edge is opposite to each other. Okay, so so this is the idea of compatible orientation. All right. Another way to sort of think about this is that if you had something like a Stokes theorem, then the net effect of having these things be opposite is that you know, it's like the contributions of the interior edges basically cancel out, right? You have an integration down this way, and the one opposite, they give you answers which are the negative of each other, they will cancel out. So all the interior things will cancel out. Okay, so that's one of the reasons, for example, why you want to have this kind of, you know, consistent orientation is because you want to be able to do things like integration of differential forms on sort of manifolds. Okay, so this is again what I call consistent discretizing, consistent orientation. Okay, and then of course it's like what happens then is that you know, a manifold is orientable, in particular if it has a triangulation which is itself orientable. And what it means for a triangulation to be orientable means that you can assign to each and every single triangle, it's like in the orientation, in each and every single one of the triangles in the triangulation, one of these orientations, and you know, they are always, it's like compatibly oriented. Every adjacent triangle, it's like in the triangulation, is always compatibly oriented in this sense. Okay, so that's sort of the natural notion of consistent orientation. All right, so let me stop here for a minute.